Let's build a Markov chain model in Python so you can better understand how it works. You can think of a Markov chain as a simulation of a system that moves step by step through time to illustrate what state the system is currently in. And all its calculations are based on one simple rule. Let's break this down. First, imagine that you have a finite list of states that completely describe the possible situations the system can be in at any given time. In a simple weather example, you might decide that the only two relevant states are sunny and rainy. Each day, the system is exactly one of these states, and there is no in between. The time is represented in discrete steps, for example, day 0, day 1, day 2, and so on. And with each passing day, the system may stay in its current state or transition to another state. Now, for each state, you specify the probabilities with which the system will transition to each possible state the next day. So if today is sunny, you could decide that there's an 80% probability that tomorrow is also sunny and a 20% probability it will be rainy. But if today is rainy, there's a 40% chance tomorrow will be sunny and a 60% chance it will continue to rain. Remember, these probabilities must always sum to 1. The central Markov property can now be stated precisely. Let x sub 0, x sub 1, and x sub 2 represent the state at day 0, 1, 2, and so on. Now this part is important. The Markov property states that the conditional probability of the next state depends only on the current state for all times t and all chosen states. In other words, once you know the current state, the entire previous history will no longer influence the distribution of the next step in the model. The past still indirectly matters because it influences which state you are in now, but once the current state is fixed, the way you got there is irrelevant for predicting the next step. This is what a Markov model gives you at the most basic level. Now, if you want to look more than one step into the future, like most data scientists do, you can combine these one-step probabilities. For instance, suppose today is sunny and you want the probability it will be sunny 2 days from now. Stay with me here. There are 2 different ways that 2 days from now can be sunny. One possibility is that tomorrow is sunny and the day after that is also sunny. Let's try to find the probability of this very first scenario. Well, let's think. What is the probability that today is sunny? Well, that's just 1 because in this scenario we are 100% sure that today is sunny. We're living in it. Now the probability that tomorrow is sunny. Well, as we talked about earlier, there is an 80% chance that we will transition from a sunny day to another sunny day, so we denote that as 0.8. The same logic follows for the day after that being sunny. There's an 80% probability for a sunny day to a sunny day, so that's also just 0.8. Multiplying this together, we find there's a 64% chance that this first scenario of 3 sunny days in a row will happen. Still considering that we just need the day after tomorrow to be sunny, another possible scenario is that today is sunny, tomorrow is rainy, and the day after that switches back to sunny. We follow kind of the same logic here. We absolutely know that today is sunny in this scenario. Now, we discussed earlier that the probability of it switching from sunny to rainy is 20%, so we denote the probability that tomorrow is rainy as 0.2. And lastly, we also established earlier that there is a 40% chance that the state switches from rainy to sunny. Multiplying this all together, we get an 8% chance for this certain scenario. So we have these 2 possible scenarios that could take place if we want 2 days from now to be sunny. Adding them together, we get a total 72% chance that if today is sunny, 2 days from now will also be sunny. And that is a Markov model for you in its simplest form. In general, multi-step probabilities in a Markov model are summed over finding all of the possible paths you can take to get to a certain goal and multiplying by the probabilities of each transition along the way. Speaking of, the probabilities that we multiplied by based on the likeliness of each transition are called transition probabilities. And to organize the information in a Markov model mathematically, all of the transition probabilities are typically collected into a single square matrix called the transition matrix. If there are n number of states, then the transition matrix will be an n by n matrix, where each value is the probability of transitioning between 2 given states. In our example, this 0.8 illustrates the probability of transitioning from sunny to sunny. Even though a Markov model can seem complicated, they are one of the most useful tools data scientists use on a day-to-day basis. So if you want to see this coded out for you in simple Python, then stay tuned for part 2.